Okay, so starting with chapter 5, we're getting into a huge change in our class. We're really going to focus today on area underneath the curve. And I think you know immediately that if your curve is not one of a familiar geometrical kind of a shape, like a semicircle or a straight line that might somehow form a triangle or even a rectangle, if you have a curve that's more of like a parabola or a cubic function or a sine wave, finding the area is going to be quite different. You never learned formulas in geometry to help you with that. And today we're going to not find the exact area, but find an approximate area. Our learning target is I can approximate area under a curve with LRAM, RRAM, and MRAM. And immediately that can sound very obscure. You can think, LRAM, what on earth would that stand for? It's actually going to stand for a left rectangle approximation method. The RRAM means right rectangle approximation method, and the MRAM means a midpoint rectangle approximation method. So here's what we're going to do. We do not have standard geometrical shapes. So what we'll do instead is we're going to say break up an X interval. We're always going to be asked to find the area on a closed interval, and it might be from A to B. What that's really asking you to do is saying, look, as X is between A and B, would you find the area underneath that curve bound with the X-axis? The area underneath the curve bound with the X-axis. You can think, well, my gosh, how do you do that? Well, we're going to break this X interval into N subintervals. What that really means, guys, is we're going to work with N rectangles. You see, we're going to do the best that we can at this point. We're going to say, well, wow, I don't have a geometrical formula, for these shapes. They're very different. What I'm going to do instead is I'm going to say, well, what if I just build N rectangles up to the curve? And the rectangles are going to have the same base today. We're going to say every time we go ahead and we make rectangles to approximate area, every single one of them will have the same base, or you could call it a width. This formula that I have highlighted is super, super important. You want to have that memorized because you're really knowing that that base of the rectangle, which we're going to call delta x, is the left endpoint minus the right endpoint, b minus a. That's the length of the interval, divided by the number of rectangles that you'd like to have. And if you think about it, I hope that makes perfect sense. You'll say whatever b minus a is, that's the length of that interval. And now I'd like to build n rectangles with the same width. Well, I'll just divide by n and I'll have the same base every time. Well, all of a sudden kids can look at this LRAM, RRAM, and MRAM. And that can seem very, very obscure with this formula right here. You can see the Greek letter sigma. The Greek letter sigma is just telling you we're going to add a whole bunch of rectangles. We're going to add a whole bunch of rectangles. The Greek letter sigma is kind of like their Greek letter S, S for sum. And you're always going to have F inside of sigma. That's going to determine the height of your rectangle. And then you're going to multiply that times the base. The base, as we said, is always delta x. And I hope you know that whenever you take the height times the base times height, that's the area of a rectangle. Well, look, I think right now the best thing we can do is actually see an LRAM in detail. You can say, well, wow, here is this curve. Obviously, it could be from a polynomial. It might be coming from a trig function, for all we know. And you begin to look at that. You'd say, well, I want to find the area underneath that curve. Now, please understand, I don't want you to lose sight that really what we're doing, what we're trying to find, would be in green here. We will learn how to do this by the not too far distant future. We'll be fine with that. But for the moment, you'd say, well, wow, I can't find that area. I don't know how. But what I could do is I could build some rectangles. I'm just going to build a whole bunch of rectangles. I'm going to make them have the same width. Now, immediately you can think, well, how do you know how tall those rectangles are? Well, this is what LRAM is all about. LRAM says when you are looking at one subinterval, the left endpoint will determine how tall the rectangle is. The left endpoint of each rectangle will determine how tall that rectangle is. And it's always base times height to find the area of a rectangle. So that's physically what's happening. Now, if you were to build these rectangles, does it look like we'd have too much area or too little area if we just kept building them and adding them up? What do you think? Too much. The rectangles are going above the curve, aren't they? So we'd get an estimate, but we'd say, wow, you know what? This estimate's going to be too big in this instance. That area of the rectangle, it's creeping over the curve. I'm getting too much area. Now, by way of comparison, you can say, well, what if, instead of doing LRAM, what if we revisited this curve and if we said, how about instead of the left endpoint on a subinterval, like look, here's the base of my rectangle, just drawing one rectangle. By the way, that's an important strategy. We always would like to draw one rectangle, bare minimum, to help us see how to do the problem. But look, as you just look at one rectangle, you could say, well, again, I know my base is always delta x. It's always b minus a all over n for each and every one of those rectangles. Same base. But now what about the right endpoint? What if it was the right endpoint that determined how tall my rectangle really went? Now, as soon as we're talking about how tall you're going, you could say, well, wow, that's a y value. Yes, that's a function value. It's a function value that's found by plugging in a right endpoint. And that would get us another approximation. Do you think this approximation would be too big or too small? Too small. You can see immediately there's, what the author did is he drew in that darker shaded region right in here. Maybe I'll color it yellow right in here. You'd say, wow, the rectangle doesn't go up high enough, and you're missing all that area for each rectangle. Your area is too small as you add up all those rectangles. Yeah, but at least we have an intelligent guess. Now, by way of comparison, you can say, now, wait a minute. You talked about LRAM, you talked about RRAM, MRAM. How do you determine that? Well, same issue, guys. You've got this rectangle. But what if instead of a left or a right endpoint, what if we took the midpoint on that interval? What if we said, don't make the left endpoint or the right endpoint determine the height, just calculate a midpoint. And if you went upwards, you'd say that red dot up on top would now be the height of my rectangle. That would tell me how tall my rectangle should be. Now, this is a very interesting rectangle, because I think immediately some kids are going to say, ooh, look, the rectangle right over here where I'm pointing an arrow, it's going above the curve. That means you've got too much area. But just over here to the left of that red dot, you'd say, well, there my rectangle is a little bit below the curve. And then you'd say you've got too little area. Well, this seems to be a really nice way to be able to come up with a good estimate. And all three ways are valid. The College Board will ask you to do problems with LRAM, with RRAM, and with MRAM. All three. It's not like they'll say, oh, we're only going to do MRAM. No, we're going to do all three. But this is just the preliminary point. You're going to notice that all of these methods look oddly close. They all have a sigma. saying you're going to add up a whole bunch of things. What are you adding up? You're adding up a whole bunch of height times bases. You're adding up a whole bunch of rectangle areas. So I wanted to talk you through that first. I think, like the sigma notation sometimes can scare kids a little bit. But ultimately, all we're doing, guys, is we're going to add up a whole bunch of rectangle areas. What we have to pay attention to is how we determine the heights of those rectangles. So we're going to go to example 1. And we're actually going to do each of those 3 types of problems. This is a very calculator-based type of activity. The calculator is really going to help you out a lot. So before we go much further, let me just state the obvious that your A here is 1 and your B is 5. You have a parabola. You have a parabola, so this is not a standard geometrical shape. And it's not a bad thing to even begin to say, let's begin to graph this thing. We could say, here's 1, and we can go all the way out to 5. But suffice it to say, a parabola that is going to, come this way, and maybe 5 is just like so. So obviously our parabola is going to grow and grow and grow. But what we're really trying to do is find the area underneath that curve. Now, maybe I could even squeeze that in a little bit just to make it look a little bit nicer. But suffice it to say, that's a little bit nicer. You can say, well, I'm going to build 8 rectangles. Yes. Let's talk about the base of the rectangles. That's delta x. What was that formula again? B minus A, the length of the interval, divided by how many rectangles I'd like to build. So real quickly, you could say, well, delta x is equal to, well, this would be 5 minus 1. And then we divide by 8. And this would be 4 all over 8. And really quickly, you'd say, well, my goodness, that's just a half. And, you could say, well, here's 1.5, and here's 2. Here's 2.5, and here's 3. Here's 3.5, and here's 4. And maybe I'll move that over even a little bit. You get the idea. Do you have to make a perfect picture here? Trust me, later on, they're going to ask you even crazier things to do, like draw 16 rectangles or 20. You're not expected to have to draw all those in. I want to be super, super clear on that. But right now, if I were to do an LRAM, I guess what I really, really, really want to point out to you is that for any interval, and I'm just going to draw my first rectangle. My first rectangle would have a base that goes from x equals 1 to 1.5. And by the way, my last rectangle would go from 4.5 to 5, if you're thinking about just delta x going that way. Which endpoint, again, determines the height? The left. So look, I'm not asking you to draw every little rectangle. But it is helpful to at least draw one. And in fact, it's helpful to draw a first and a last. Now, when you draw a first and a last, I think that can really help you because you're going to realize that I'm starting with an x value of 1 for my height, and I'm ending with an x value of 4.5. And that's very important to know which x values I start and end with to determine heights. That's super, super important. So look, what we're going to do is very quickly jot down a formula for sigma. Sigma is going to be some sequence. We're going to type that out. We're going to have our expression. Then we're going to have x. We'll have start. We'll have end. Then we will have our step.